Hi class, today we're talking about section 5.6, the real zeros of a polynomial function. Now I just want to preface this by saying that there are a lot of theorems in this section. Now the first theorem that we're going to go over is just a way to understand the next few theorems. Some of these theorems I will tell you, you have to learn and you have to memorize and you have to know how to do them. And I will be asking specific questions on the test regarding those theorems. For this first one though, I'm just going to be using this to explain what's going on. So hopefully understanding what I'm talking about now will make everything else make more sense. The first theorem is about the division algorithm for polynomials, and it's a little bit confusing to look at like that. So I'm just going to ask you to simplify a fraction or to do division. If I told you 25 divided by 7, how many times does 7 go into 25? Well, it would go into it 3 times with a remainder of 4. We would put that remainder of 4 over the divisor, which is 7. And we could label all the parts. So we have the dividend of 25, the divisor of 7, the quotient is 3 with a remainder of 4. And you always put the remainder over the divisor. So we have that over here. And if I wanted to take this and rewrite this as a multiplication statement, I would get 25 is a result of 3 times 7 plus 4. And so hopefully these pieces make sense to you when you see f of x divided by g of x. That's the dividend divided by the divisor. You end up with the quotient q for quotient, q of x, plus r of x, r for remainder, over g of x. So what does this mean? Well, this is just a way to say if I have a polynomial and I divide it by another polynomial, certain things will happen. And we know what division is like when we use numbers, and we're using the numbers to help us understand what division is like when we use polynomials. But basically you want to look at this portion of it and say I have my dividend is equal to my quotient times my divisor and plus my remainder. Now, what happens if my g of x is the simple binomial x minus c? What happens when you say, what's g of c? Well, g of c would then replace the x with the c value, and you're going to get c minus c, which is 0. So I would know that g of c is equal to 0. And we're going to keep that in mind as I look at the remainder theorem. The remainder theorem says, suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Why would that be true? Let's work it out. Remember, x of c is going to be the same thing as g of x. So let's go ahead and rewrite it with g of x. If I said f of x is divided by g of x, the remainder is going to be f of c. Let's see. I say f of x is the same thing as the quotient times the divisor plus the remainder. Well, what happens when you plug in c? You would get f of c and q of c and g of c and r of c. But recall from our work on the side that g of c is equal to 0. So this is going to be equal to 0. So we're going to cancel it out. And so I end up with f of c is the same thing as my remainder. So this matches what the remainder theorem says. If I'm going to divide by the monomial x minus c, then my remainder is the same thing as f when you plug in c. Let's see how we use that. Let's go ahead and use the remainder theorem to solve question number 1. It says to use the remainder theorem to find the remainder when my function f of x is divided by x minus c. In this case, we're saying what happens when I say 4x to the 4th minus 15x squared minus 4 is divided by x minus 2. I could do the long division, and I could figure out what the remainder is by doing long division, but it doesn't say to do it that way. It says to use the remainder theorem. In order to do that, I want to use the topic we just talked about. Instead of doing long division, I'm going to say from x minus 2, my value is 2, my root is 2, and so I'm going to say what's f of 2. And if I plug that into my function, I get 4, 2 to the 4th, minus 15 times 2 squared minus 4. I would get my remainder would be 0, because by plugging it in, I would be able to see that the same result as if I did the long division. And if I ask you on the quiz, or if I ask you on the exam, use the remainder theorem, I expect to see you plug in the value into the function and say, this is my remainder, after I simplified it. I don't want to see the long division. I want to see you use the theorem that's being asked for. Now, what does it mean to have a remainder of 0? Well, let's recall what it means in division. The first example I said was 25 divided by 7. We said that was 3 with a remainder of 4. But what if instead I asked, what is 28 divided by 7? You would just say 4, and then that's it. We don't have a remainder. We wouldn't say plus 0 over 7. But if I did, my remainder would be 0. And so when it says that 0 is a remainder, it means that my divisor divides it evenly. In other words, the x minus 2 is a factor of my function. And so we would say x minus 2 is a factor of f of x. That's because I saw that 0 was the remainder. Before we go into another example, I want to just talk about this factor theorem that we just used. Remember that the word factor means that it divides a number evenly. So earlier we were saying 25 divided by 7. Well, 7's not a factor of 25. But if I was to say 28 divided by 7, well, 7 is a factor of 28. And we can come up with a phrase like 28 is 4 times 7. So that's the way 4 and 7 are both factors of 28. So remember, factor means to divide evenly. So this factor theorem says my divisor is a factor if my remainder is 0. My divisor is a factor if and only if my remainder is 0. I'm getting that from the remainder theorem. So we're sort of mixing all of the things on this page right now. You will be asked to use the remainder theorem to find the remainder, then use the factor theorem to tell me if that polynomial is a factor of our function. Now for question number 2, we're going to be doing the same steps. We're going to be using the remainder theorem. We're going to divide by x plus 1/3. I'm going to write x minus negative 1/3. Instead of doing the actual division, all I'm going to do is take that negative 1/3 and plug it into my f function. And so my remainder is going to be 2. Without having to do the division, I will know that my remainder is 2. Now tell me, if I have a remainder of 2, does that mean it divides evenly? No. And the factor theorem then tells me x plus 1/3 is not a factor of my function. So I have 2-part answer. My remainder is 2, and x plus 1/3 is not a factor. Before we get too far into this section, I want to just recall some stuff that we learned last chapter. That is, if you were given a quadratic equation, you knew how to solve for it, either by factoring, or if you couldn't factor, we could use the quadratic formula. And this quadratic formula was really important because it meant anytime I had a quadratic, I could use this formula to find its roots. I could find its real zeros if it had any. I could find its x-intercepts. And back in the day, many, many years ago, before they had calculators, before they had computers, this was the only technology that we had to find the roots. So if we had an equation and we wanted to find its solutions, this was the only way to do it if we weren't able to factor. And so then the question became, well, what happens if? What if I have something that's x to the third? What if I have a third degree polynomial? How do I factor it? How do I find its roots? And I can't apply the quadratic formula to an x to the third. Or what if I had a fourth degree polynomial? What if I had a fifth degree polynomial? And you might not believe me, but they actually had math duels. And whoever was the smartest mathematician of the day would win money, win prizes, would be revered. They would be given a problem and they would have to try to find all the roots. And so we're going to go about finding the roots even if we have a polynomial that's of more degree. So the theorems on this page are geared towards helping us find some of those roots. The first one just tells us how many real zeros we can find. It says a polynomial function cannot have more real zeros than its degree. And this one comes out of the definition that a real zero is the same thing as a factor. And so when you think about how many factors a polynomial can have, it can't have more factors than its degree. If I had a polynomial in factored form, x minus r1, x minus r2, all the way up until x minus rn, well then that would mean I would have n amount of factors, and if I multiplied it out, I would get x to the nth power plus, and I would have all the rest of the terms, which I don't know, but this would be an nth degree polynomial. So if I have that many factors, I would have at least that many degrees. The number of real zeros theorem is really nice because if I was given this problem to find all of the real zeros, I would know I'm done when I've reached 5 zeros. I wouldn't have to go around looking for more zeros than 5. So that gives me a limit for how many I'm going to be looking for. This next theorem, the rational zeros theorem, is nice because it gives me a place where to start looking for my zeros. If I know that I'm looking for 5 zeros, but I have no idea where to find them, then I could just be lost trying to plug in as many numbers as I can. And instead of doing that, what I should do is try specific numbers related to the function that was given to me. I want to look at this theorem and help us figure out which pieces we need to help us find our potential rational zeros. And what it tells me is that I want to look at my a sub n and my a sub 0. Basically, the leading coefficient and the constant. So in this question, that means I'm looking at the 3 and the 4. So it says p over q, where p is a factor of a naught. So I want p over q, where p is a factor of 4, and q is a factor of 3. It says if I have any rational zeros, then I know it will come from a combination of these. So we're going to write all of the factors of 4. Those would be 1, 2, and 4. We're going to take all of the factors of 3, 1, and 3. And we're going to make as many fractions as I can. And I'm just going to go in order methodically. I'm going to say 1 over 1, 2 over 1, 4 over 1. Next, I'm going to say 1 over 3, 2 over 3, and 4 over 3. Now, if I have any rational zeros, then it will be on this list. But I don't know if they're going to be positive or negative, so I'm going to put plus or minus 1. And so instead of having to test all the real numbers, I have a list of 12 numbers, 6 numbers with either positive or negative, and one of these 12 numbers, hopefully, is one of the roots to this polynomial that we have listed here. And so if I were to be looking for my rational zeros, or if I were to be looking for any zeros at all, this is a really good list to start. Because I don't want to just start plugging in random numbers. I want to plug in numbers that might be related to the question. And if I were to be doing this way back in the day, I would take each of these roots and I would use them, I would plug them into the function. Why would I be doing this? Well, if it worked out, I would say, well, if it's a factor, then when I plug it in, it's going to be equal to 0. That's one of the theorems we learned in the beginning, which was the factor theorem. So this is much nicer than trying to do long division. You just plug some values in and see if it works out. So now let's apply what we learned in these two theorems to question number 3. Question says, determine the maximum number of real zeros that the polynomial function may have and list the potential rational zeros. So those are two separate questions. The maximum number of real zeros matches the degree. It can't have more, but it can have up to 4 real zeros. And then it says list the potential rational zeros. So that would be looking at the first term and the last term. We want to get the factors of the last term. And we want to divide that by factors of the leading coefficient. So we're just going to make a list. I have 1 and 2 as the factors of 2. I have 1, 2, 3, and 6 as the factors of 6. Now I have 2 in the numerator and 4 in the denominator. I'm going to make every single possible combination I can. And I'm going to go in order. So I'm going to say 1 over 1, 2 over 1. And then I'm going to say 1 over 2, 2 over 2. And then 1 over 3, 2 over 3. And then 1 over 6, and then 2 over 6. When you're doing this, you want to make sure you do every single possible combination. There's 2 in the top, 4 in the bottom, and that leads me to a total of 8 possible combinations. However, some of these mean the same thing as others, because if I reduce the 2 over 2, I get 1, and 1 was already on the list. And if I reduce the 2 over 6, I get 1 over 3, which is already on the list. Is there any others I can reduce? If not, then there's my final list. So I have plus or minus 1, plus or minus 2, plus or minus 1/2, plus or minus 1/3, plus or minus 2/3, and plus or minus 1/6. And so these are my potential rational zeros of this function. Question number 4 asks us to use the rational zeros theorem to find all the real zeros of each polynomial function. What it does not say is that after you find your potential rational zeros, you need to use the remainder theorem and plug all of those rational zeros back into the original function, and then use the factor theorem to see when you plug those in, does it make the function equal to 0. And then if we find a factor, then what we want to do is divide this polynomial by that factor to come up with a reduced polynomial, which would be easier to find more roots to that. So we'll go through the steps together. Let's first start off with finding all of our potential rational zeros. Oh wow, that's a lot of factors. A few of them do cancel out. The 3 over 3 becomes the 1. And then I also have 6 over 3, that becomes a 2. And then I also have 15 over 3, that becomes 5. And then I also have 30 over 3, which becomes 10. So I get 4 less factors. I'm going to take all of these factors and plug them in. So I'm looking for f of 1, f of 2, f of 3, and I'm going to keep on going. Also, don't forget that each of these, we have to try the positive or negative version of them. So we also need to see what's f of -1, what's f of -2, and so on and so forth. Now, this might seem like a lot, but I would bet if you were a big mathematician back in the day, you would have some helpers, and you could say, hey, helpers, do all these problems for me. Figure out which one is equal to 0. But you would have to know the rules to be able to give them that. And so I'm going to go ahead and use a calculator and fill these numbers in. And I get f of 1 is -36. So that's using the remainder theorem. I know that I know that 1 is not a real 0 of this function, because if it were, it would be at f of 1 is equal to 0. So we're going to continue plugging numbers in. And f of -1 is -12, so also not a real 0. F of 2 is -12, so also not a real 0. But hey, f of -2 is 0. So that means that -2 is a real 0 of this function. It also means that f is divisible by x plus 2. And we're going to use that to help us write a reduced polynomial. Every time you find a real 0, you want to write it as a factor and divide your polynomial by that factor so that you get a reduced polynomial, and then it'll make your list of possible rational zeros less, so you have less work to do. So if we do the division once, that decreases our workload. So I'm going to do synthetic division. Remember that if x plus 2 is our factor, then our root is going to be -2. And that's going to come into play if you do synthetic division. I'm going to put -2 outside our synthetic division sign, and the leading coefficient, as well as all the other coefficients in decreasing order of the variable. You're going to bring the 3 down, and then multiply it by the -2 to get -6. Add these terms to get a 0. Multiply it by the -2 to get a 0. Add it to the -15 to get -15. -15 times -2 is +30. Add that and you get 0, a remainder. So the piece is that this was the x plus 2. And then this portion becomes 3x squared minus 15. Now remember, I just did synthetic division. If you don't know that, then you can do the long division. And if you don't know that, I will be making a division video so that you guys can practice these methods. But you have to know how to do the division of polynomials. And then I can factor this out a little bit more. There's a 3 in there. That's 3 times x plus 2 times x squared minus 5. And I'm going to factor that one more time. That's going to be x plus radical 5 and x minus radical 5. I only had one rational root. That rational root is -2. The other two are irrational. I have negative radical 5 and positive radical 5 as some of my roots. So even though we used the rational zeros theorem, we found all the real zeros, like the question asked about. All the real zeros are -2, which is our rational one, negative radical 5, and radical 5 as our irrational ones. And then we've also done the factoring over the real numbers, like the question asked, and so we've done everything that we've been asked to do by finding the real zeros and by factoring. Question number 5 has the same instructions as question number 4. That is, we're going to start off by using the rational zeros theorem to find all of our potential rational zeros. We're going to use the remainder and factor theorem to plug all those potential rational zeros into the function and see which of those will cause the function to be equal to 0, therefore which one of those are actual real zeros. And then we will factor or divide our polynomial by those factors as we find them to help us come up with the simplest version of this polynomial. Let's go ahead and get started. Looking at the factors of p, which is 8, and the factors of q, which is 1, we get 1, 2, 4, and 8 divided by 1. So we only have those 4 options, or rather 8 options, if you consider the plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8. So let's go ahead and set that up to plug those into the function. So we're going to take all of these 8 factors and plug them into the function and see what results we get. Because if we know the results, we know the remainder, and if the remainder is 0, then it's a factor. I went ahead and used my calculator to help with this process, and when I found f of 1, I got 6, and when I found f of 2, I got 0, which means that 2 is one of my real zeros. So we're going to go through the process of doing division to get that factor of x minus 2 out of this polynomial and get a reduced polynomial to then further this process. I've set it up to do synthetic division again. My real zero is 2, and so I'm going to put 2 outside the synthetic division sign. I'm going to bring down the leading coefficient of 1 and multiply that by the 2. I'm going to get 2. Negative 1 plus 2 is 1. 1 times 2 is 2. Negative 6 plus 4 is negative 4. Times 2 is negative 8. 4 plus negative 8 is negative 4. Negative 4 times 2 is negative 8. And then that adds together to make 0, which is great because that's my remainder. And once again, that's going to be x minus 2. And then the second one is going to be representative of x cubed plus x squared minus 4x minus 4. And then we can do this again. So looking at what I've underlined as g of x, we call that the reduced polynomial because it is our original f of x polynomial divided by x minus 2. That's the polynomial that comes out after we've done the division. And I'm written in here the factors of group 4 over the factors of 1, and I've come up with 6 options, plus or minus 1, plus or minus 2, plus or minus 4. And so I'm going to take all of those options and plug them into my g of x polynomial, aka the reduced polynomial. I'm going to see if I can find another factor. And plugging 1 into this function gives me negative 6, so that's not a factor. Because g of 2 is 0, that 2 is a real 0 of this reduced polynomial, and therefore we can divide this polynomial by x minus 2 to get another reduced polynomial. Let's go ahead and do that with synthetic division. Remember, we put the real 0 on the outside, so we put the positive 2, and then we put all of the coefficients down, 1, 1, negative 4, negative 4, bringing down the 1, then multiplying by the 2, adding them together, multiplying by 2, adding them together, multiplying by 2, adding them together. I'm running a little bit out of space, but this first x of minus 2 comes from the first time we did this, and then we have the second one comes from the second time we did this, and then each of these coefficients come from doing the long division, and my remainder is 0, so I don't have any more remainder. Now I have here my 2 factors that I found and my reduced polynomial. And if I wanted to use the rational zeros theorem again, I could. However, you should notice that we do have a quadratic, and that's something that's easily factored. So let's go ahead and just factor it the way we've learned in the past. And there we go. We found all 4 factors of this 4th degree polynomial. Let's just write it one more time to make it in better form. And there you have it. There's our polynomial function that got factored. It did ask us to find all the real zeros, so let's go ahead and list them. The real 0 of 2 with a multiplicity of 2, a real 0 of negative 2 with a multiplicity of 1, and a real 0 of negative 1 with a multiplicity of 1. Recall that when we have the real 0 and we have the factors, they're going to be opposite signs. That's why we have negative 1 as a real 0, but x plus 1 as a factor. You have to make sure that you always change the sign when you do that. Now question number 6 asks us to find the real solutions of the equation. But if you recall from a previous lecture, to find the real solutions of an equation that is equal to 0 is the same thing as saying what are the x-intercepts it's also of the graph, it's also the same thing as asking what are the factors of the polynomial. It's also the same thing as asking what are the real zeros of the function. So we can just call the left side of this equation f of x, and then we can apply all the rules that we did last time. So first I'm going to look at the rational zeros theorem. And we can find all the possible factors by getting the plus or minus 1, plus or minus 3, and plus or minus 9. We get this from the factors of the last term divided by the factors of the first term. And let's go ahead and plug those into our function. I'm going to use my calculator to help me figure this out. Right away, when I plug 1 in, I get f of 1 is 0. Let's go ahead and do the synthetic division. Bringing down the first one, we get 1 times 1 is 1. Add these together, we get negative 1. Multiply by the 1, we get negative 1. Add those together, I get 9. Multiply by the 1, add those together, I get negative 9. Multiply by the 1, add those together and get 0. So this first term is x minus 1, then all the rest of it becomes x cubed minus x squared plus 9x minus 9. And then we're going to go ahead and do the rational zeros theorem again. We basically have the same factors. We have factors of 9 divided by factors of 1. So we have 6 possible rational zeros again. And when I'm using my calculator, I find that f of 1 is equal to 0 again. So that's another one that I'm going to use. And we're going to do synthetic division again. We want to now find the factors or any real zeros to this cubic polynomial. Let's nickname it g of x. We can't call it f of x because f of x was our original polynomial. So we just want to give it a nickname. That's going to be our reduced polynomial. As we want to find the zeros, we're going to look at the factors of 9 over the factors of 1 again. And we've done this before, so we should know already that we're going to be plugging in plus or minus 1, plus or minus 3, and plus or minus 9. And we go ahead and use the calculator. We get g of 1 is equal to 0. So that's going to give me another real zero or another solution to this polynomial. And as I do the synthetic division again, I bring down the leading coefficient, which is 1, multiply it by our real zero of 1, add them together, multiply 0 times the 1, add them together, multiply the 9 times the 1, add them together, and this is what I have left. So let's see, where do all the pieces come from? So I'm going to get this x minus 1 comes down. Here's another real zero, which turns into another factor, another x minus 1. And then I have this portion here, the result of the synthetic division, and that's going to be x squared plus 9. And so we're going to call this one h of x. Our reduced polynomial will be h of x. So now we want to go on to find the factors of h of x. Because we have the same leading coefficient and the same constant, we still are looking for factors of 9 over 1. We're going to plug in the same values, so I didn't bother making my list again. But we're plugging them into my reduced polynomial, my h function. And when I plug them in, I get 1 squared plus 9. And negative 1 squared plus 9, 3 squared plus 9, and negative 3 squared plus 9, and then 9 squared plus 9, and negative 9 squared plus 9. And none of these are zeros, so we don't have any more real solutions. I factored the equation, and the equation factors to x minus 1, x minus 1, x squared plus 9. Well, this one has a real zero of 1, this one has a real zero of 1, and this one has no real zeros. This one has no real solutions. If you recall, this is prime, it would have imaginary solutions or complex values if we use the quadratic formula to find it, but it doesn't have any real solutions, which is what we were asked to find. And so we only found 2 real solutions for this 4th degree polynomial. Since we were asked to find our real solutions, we found it. Now you could put 1 and 1 into the real zeros, or you could say, well, I have 1 with multiplicity 2 into our set notation, but we can't put any of the solutions from here in because those are not going to be real. They're going to be complex. And we're actually going to look at that in the next section. So we're going to be doing all the same stuff that we did in finding the real zeros with an extra portion, which is also how do we find complex zeros. Looking forward to section 5.7. Thank you. Have a good day.